Hello? Okay. Hello and a good afternoon. Thank you for joining me for this presentation regarding the industrial application of fiber optic FBG sensing systems. My name is Tomas. I'm a project engineer from a company called SYLEX, and I'm not sure how much time we will have for any questions after the presentation, but we have a booth here in the second hall, so you can join us and we can discuss everything there. A very short introduction to the company. SYLEX is a mid-sized company based in Slovakia with more than 28 years experience in fiber optics and more than 15 years experience in fiber sensing using the FBG technology. Now the FBG technology, most likely everyone knows what I'm talking about, but just to make sure, the FBG technology or the FBG, the fiber back grating, is a local modulation of the refractive index inside an optical fiber. You can imagine that as a structure which is inscribed inside the optical core and creating something like a mirror, which is reflecting a particular wavelength. So if you will inject visible light inside the fiber, it will reflect just the yellow color. If you will stretch it and the points, the inscription will go apart, it will reflect, for example, a red color. And these wavelength shifts are proportional to strain. So just by using the FBG, the optical fiber, you can measure strain, and if you can measure strain, you can utilize the technology to measure all other parameters, including temperature, pressure, displacement, or even chemical-based sensors like for hydrogen or humidity. The fiber optic technology has several advantages compared to the conventional technologies like vibrating wires, for example. And that's the chainability of these sensors. So if you have different sensors at different wavelength, you can chain them together, which will make the cabling much more easier. The technology is electrically passive, so it's immune to electromagnetic field. And there is as well a variation of optical fibers that you can use for the application. So if we speak about the basic telecommunication fiber for single mode, which is designated as 9/125. This can be used for inscribing the FBG. Smaller cores can be used, larger core fibers can be used. Different coatings can be applied to the fiber for the application you're looking for. Basic polymers like acrylate, polyimide, armature, even carbon-coated fibers or metal-coated fibers. So it's really about the application you are looking for, and the FBG or the optical fiber with the FBG can be utilized for that application. Now I've divided the presentation into several slides describing fields of the application. I will tell at each slide why it's important to apply the sensors there, what are the challenges and what are the responses. I will stop at few slides for a bit longer. Some I will just skip quite quickly. But again, if there will be any questions, I can answer them later on. Fields like energy and industrial automations. Nowadays, energy and especially renewable energy is growing every year. And all these structures which are deployed and the wind turbines that are deployed over the world should be monitored. And the reason why is first to protect the asset, and by second to increase the efficiency of the wind turbines. If you will place a sensor on top of the blade of a wind turbine, you can measure the stress coming from the wind reaching the turbine or the blade, and by adjusting the angle of the wind turbine you can increase the efficiency. So the outcome is as well commercial, and as well if you sense vibrations on a blade which are unwanted on the wind turbine, you can as well stop or slow down the wind turbine just to protect it. These structures are tending to fail, and the importance of monitoring has as well commercial and protection reasons. Adding a sensor on a wind turbine has some limitation. The lightning protection which is there doesn't allow anything from metal to be placed on top of that. The sensor needs to be low profile, just not to interfere with the aerodynamics of the blade, and has to have very easy installation to make it fast, and in most cases on a turbine which is already in place. The FBG technology, as already mentioned, since it's electrical passive, it's allowed to be placed on top of the turbine, on top of the blade, and the sensor itself can be made completely dielectric. I have an example there of one of the sensors in the right corner. It's a completely composite-based sensor without any metal inside that can be glued on top of the blade. The sensor is double-ended, so it can be chained, and just one fiber is then dragged to or run to the center of the wind turbine for monitoring. Industry automation, that's a different field. Nowadays, a lot of companies are replacing the manpower with automation, so all the production lines are replaced with something which is automatic, and the reason for that is to increase the profit. These lines are designed to be operational 24/7, and in the moment the line is not operational because of unwanted maintenance or any kind of damage, the company is losing profit. Using the fiber as it is, because we are speaking about a structure which can be small as 160 micrometers in outer diameter, it is possible to retrofit, or even by production of these automation machines, equip certain parts of the production line with sensors that will predict if the machine is or should be under maintenance or not, and prevent unwanted stops of these machines. Usually, if people are referring to monitoring or sensing, they're usually thinking about structures like bridges and buildings and the basic engineering structures which are all around us. The reason why to monitor these structures is simply because even though someone is designing these structures for a certain lifetime, certain use, there is no way to predict how the structure will behave and under what condition it will be in 10 or 20 years. Areas with no seismic activity can be active in 10 years, and this is heavily impacting the lifetime of these structures. One way of how to verify or distinguish if the structure is still in a healthy state, if the dynamic response of a bridge is still fine or not, is to equip them with sensing solutions. That can be, of course, any technology, but the fiber optic solutions is making the installation and deployment of this sensor much easier. And it's again because of the cabling. You can imagine that if you want to deploy hundreds of sensors on a bridge, during construction or after construction, you can drag hundreds of these sensors with using just one cable to the interrogator room with the data logger. The cable with an outer diameter of around 7 millimeters can include as much as 24 fibers, and every single fiber can be used to connect to several chains of sensors that are at different segments of a bridge, for example. And in the end, you are running along just one fiber or just one cable along the bridge compared to other technologies where you need to drag one fiber to a certain sensing point. Next advantage here on this structure is as well the design changes that can be done to these sensors. Now the sensor can be small, the gauge length of these sensors can be small as a few centimeters up to several meters. The installation technologies are as well absolutely free, so at some point you can bolt the sensors to a structure, you can glue them, you can spot weld them. Different application requires different sensing approach, and due to the universal application and design of the sensor, it's possible. Next to the buildings which are above the ground, very important part of monitoring as well, the foundations which are created before. Before the sensors were, let's say, I will not say fragile, but not so robust, since at most of the structures where the sensors are deployed, some visual appearance should be set. That means that they shouldn't interfere with the visual appearance of the structure where they are deployed. For geotechnics or soil mechanics, the sensor has to be robust as much as possible. And if you imagine that we are still speaking about optical fiber, which is made from silica, so it's glass at the end, these sensors can be utilized to withstand extreme conditions, heavy pressure, heavy load, and even possible to be modified to measure, for example, load and a retention wall and very similar applications. The same applies to landsliding, for example. Landsliding is something which is quite often happening around the world. There are several methods of how to measure that. One of the methods is to drill a borehole and insert inside a sensoric chain which is measuring the different layers of the soil. And that's possible to do with fiber optics, where in this particular case, all the sensing points can be at one fiber. So you are still having just one cable which you are inserting inside the borehole, which is saving a lot of time by drilling the borehole and as well the installation itself. A separate field of application is marine application. That's something where huge structures are present, but the problem by these structures or this application is that they are inside a very hostile environment. Sea applications are having two main aspects. First is seawater, which is definitely hostile to most of the materials we can use on shore. And the second is the installation of these sensors. The installation is usually done offshore, which means that the installation is done probably by divers or by robots underwater. In this case, again, the robustness of the sensors is necessary to be made, and as well the cabling of the installation is very important. So in this case, designing a sensor which is very easy to be installed, very easy deployed under seawater, and as well simplifying the cabling can save a lot of money during the application. And the sensors, of course, can be utilized to withstand the hostile environment, and as well to be deployed, for example, on oil rigs and even on tankers. Now, for tankers, that's quite an interesting topic, because for tankers, you can measure quite easily the deck. So because the ships are too long, if they are reaching the water, the waves, they can bend in the use. So you can measure the deck just to see if the bending is still acceptable or not. But what is important here is to measure the flow or the pressure coming from the water at the front side. If you can measure the pressure on the front side of a ship, you can adjust the curves of the ship to make it more efficient and most likely faster and consume less fuel. The subsea environment includes as well structures which are already in place, so not only structures which are above the seawater or sea level, but as well pipelines or risers which are inside the water already deployed for several years. So retrofitting a solution which is our structure, which is already in place, it's not an easy task. Again, the installation, the robustness of the sensor, again, the cabling, it's very important to have it as simple as possible. I have a picture of a sensing belt here that was deployed on a pipeline, and the belt was deployed on a pipeline which was 30 meters underwater, so the only installation possibilities were by divers. The divers are having most likely no experience with fiber optics or any sensing technology, so the handling of the sensor, the handling of the design needs to be modified in a way that it will withstand these installation conditions. So of course possible in the means of the design, but every single belt had 5 displacement gauges around, 1 temperature gauge, and everything was connected through one fiber to the interrogator that was on a buoy several hundred meters away from the location of measurement. If I was speaking regarding the renewable industry and especially wind turbines, these are deployed not only onshore but as well offshore. Few options how to deploy them offshore is either to do a floating foundation or to hammer a pile into the soil or to the seabed and place the structure on top of that. Very high shocks, we are talking about shocks that are reaching thousands of Gs, very high frequencies, thousands of hertz, or something very special for the sensing solution that could be applied during the hammering process. And the hammering process needs to be monitored. And that's because even though anyone do a geological survey of that area, there is no chance that they will pick up the exact location where the pile will be hammered at the end. So avoiding hammering the pile into the rock bed, for example, or at the end having some information what could be the pile load at the end is necessary. And the only option how to do that is to do by monitoring. Conventional methods for monitoring include the monitoring on pile top, which is quite easy. You can place the sensors on the pile top, and then you are just hammering the pile down, or around the pile shaft, down to the pile toe. The problem with the conventional sensors here is that they are having quite a big size. Let's call it like that. They are quite large. Again, the small size of the fiber optic, not cable, but the fiber itself is having a great advantage because it's possible to attach the fiber directly to the surface of the pipe from pile toe to pile top, cover it with very simple protection and having a minimal protruding from the pile surface to allow it hammering down to the soil. And this is possible to be done around the wall pile without any extra shielding or anything like that, which means that it will save a lot of troubles during the construction or preparing of the pile. Like this, you can have monitoring of a pile driving not only on the pile top, for example, but as well on the wall pile shaft. So the sensors are not only for, let's say, static measurement like the bridges or low vibrations, but as well they can resist an extreme shocks and as well acceleration that is present by this kind of measurement. Pile driving is one way of how to create a foundation. The second way is to create the piles from concrete. Of course, this is something which is done very often, for example, for bridges. And most of these piles created from concrete, especially in Germany, are monitored. All of them are tested for load. That's important again. Anyhow, you will plan the construction of these kind of foundations. There is always a risk that after the construction, the pile load could be lower than expected. And this is something you need to prevent. And this is why they are, after construction, they are loaded with very high load jacks to monitor if the pile will withstand the load. And the monitoring inside is especially for monitoring cracks inside the concrete pile. So I was speaking already about C applications of pressure resistance. Now the pressure is generated by concrete, so the fiber optic sensors can be deployed even in these environments with designs which are allowing to measure the behavior of the pile that is created and loaded later on, but as well with a simple adjustment as well along the profile of the pile. Structures which are already in the soil, like pipelines, they can be as well above the soil, but usually beyond the soil or below the ground. They are susceptible to landsliding, especially. They are susceptible to any construction which is done near them. And what can happen is, of course, if there is a pipeline which is acting like a robust structure inside, and movement on soil will be present, it will go to stress on the pipe itself, and it can yield even to a breakage, so a leakage at the end. And I will tell it again, the chainability of the sensors is a huge advantage of this technology, because not only you can have sensors which are possible to be applied during the operation of the pipeline, there could be glued, there could be spot welded, because the spot weld energy is very low in that case, but all the segments which will be monitored can be interconnected with, again, one cable and then dragged down to one room with the interrogator. And this is simplifying very much the installation itself, and as well the necessity of dragging or running cables around the soil, because if there is something already in the soil, it's not easy to uncover everything. You're usually uncovering segments which you want to measure or monitor. So the rest of the pipeline is inside the soil. So running a cable or bunch of cables on the pipeline isn't possible anymore. So the chainability, running the cable inside the ducting beneath the soil, that's possible with fiber optics, and as well the variation of sensors that can be adjusted from axial strain to rosette configuration is as well an advantage that can be applied here. Some applications requires only sensing systems that are electrically passive, like servo monitoring. That's something where no electric signal can be present. So the only option is to have electrically passive equipment inside, and as well the sensors. Since fiber optics is electrically passive, it's ideal for monitoring sewers, for example. And in this case, it can be anything from humidity, temperature, it can be the circumferential profile of the sewer, or it could be as well the stress inside the walls. Anything like that can be measured with fiber optics. And the reason why to monitor that, of course, it's again constructions. It could be age, of course, but it's usually constructions which are nearby. So when you are drilling another tunnel, for example, near a sewer which was built 50, 100 years ago, there is a high risk that the structure will collapse. And it will not do damage only beneath the surface, but if the sewer will collapse, it will most likely result as well in collapsing the road above that. So the fiber optic technology, again, because it's electrically passive, can be deployed there without any issues. The easiness of cabling will again make a big difference, because all the rings which are there at one image of the segments can be interconnected together, and just one cable is then coming from 10, 20 sensors to some meeting point from where it's going to the interrogator. Process control in industries, high temperature, vibrations, and so on. So for example, steel industry, which is processing metal, this process is handled by a reactor in which the metal is processed at the end, and the reaction should be controlled. If the reaction is not controlled inside the reactor, it may happen that the product at the end is not something you would like, or it will get damaged because of the temperature wasn't right or the profile wasn't right. Fiber gratings can be used in a chain. The sensor can be made small as 1 millimeter for application reaching temperatures up to 600, 700 degrees. So you could imagine that you can have a very small capillary with an OD of 1 millimeter that could be along 10, 20 meters with 20, 30 sensing points at one fiber that can measure profile on these steel reactors, for example. And this will then help to control the process itself, and as well protect the asset as the reactor. Another field is big science. So I was speaking about the renewable energy. Another aspect of energy industry is as well the future energy. So we have already for a few years in development, many years, hot fusion. The reactors have to be monitored. The experiments are having some theoretical foundations. The best way of how to supply some additional data or to verify if the theoretical assumptions are right is to measure them. Low, high temperatures by these experiments, high radiation, strong magnetic fields. Again, it's impossible to deploy any other technology there than fiber optics, which is immune to that. And on top of that, you can get fibers which are specially designed to withstand higher radiation, so-called radiation-hardened fibers, to have longer lifetimes. And at the end, if you have the right solution, you can monitor from vibration, stress, as well temperature in these reactions. And this includes, for example, the hot fusion reactors, and as well high energy accelerators like in s.r.o. that could be as well equipped with these kind of sensors. And because of the conditions like the strong magnetic fields, it's not possible to deploy anything else. Now very quickly regarding some bigger structures like dams. Now dams are civil structures as they are. There could be, and they are, retrofit with fiber optics for monitoring the galleries, to monitor how the dam is expanding during summer and winter. That's possible again, and the installation conditions and the installation way can be as well modified to meet the expectations. If there is no chance to drill inside the wall of a dam, it could be even glued at the end, or some alternatives can be made up. It can be embedded at the end. So the monitoring of these large structures like dams is possible as well with fiber optics. Again, the chainability is a big advantage here, and as well the variation of the sensor themselves is something that can always meet the expectations of the customer at the end. Very shortly regarding this, dynamics and vibrations that we are seeing like every day, like by trains, for example, the pantograph, which is pushing against the high power wires above him. Seems to be quite simple, but this is something which is monitored as well. Now it's about the pressure or the force which need the pantograph to generate to touch the high power wiring above. As well, the vibrations of the rails. That's important to monitor as well. The rails are expanding during summer and contracting during winter. It's very important to monitor if the junctions of these rails are not failing or not, because if they will fail, there is, for example, a very high release of stress inside the rail. If it will be not picked up, there could be quite a disaster. And the same applies for bridges. Bridges tends to, after some time, changing their dynamic performance or dynamic properties, and if they will reach, for example, the eigenfrequency, that's already a disaster. So monitoring basic structures we know from our daily life, like the bridges, the rail wheels, and it doesn't matter if the bridge is for cars, pedestrians, or even for trains. That's something which is necessary to be monitored. And the main reason for monitoring is protecting lives, but as well protecting the asset or prolonging the lifetime. And for railways, for example, for the pantograph, again, the high power voltage wires which are lines which are above, there is no chance that they could go any other technology than fiber optic, which is electrically passive. And since the body of the sensor can be utilized to be the electric as well, it's even better. And the cables are, of course, the electric. Could be conductive, but in most cases, they are the electric. To make a short conclusion regarding this, there is most likely no field where the FBG-based sensors are not possible to be deployed. The applications are reaching for simple R&D project through medical applications, aerospace, civil structures, more or less anything. And since the fiber itself can be utilized, different types of fibers and coatings can be applied to that. There is as well options to modify the sensor itself to meet the expectations of the experiment or of the application as much as possible. So not just by using one product, one fiber that you have available, but as well anything that will meet the expectations a bit more, like the radiation hardened fibers as they are. So thank you for your attention. Again, we have a booth here in the second hall, so you are welcome to stop by, and if there are any questions, I'm happy to answer them here or there. We have as well some sensors there, so it could be interesting to see. Thank you.